Okay. So no questions on that? Any questions on, or any questions at all on the homework even? Oh, okay, good. This is the weird thing. I would expect a question like this. So if I give you two things like that, let's just make some different numbers up. And I ask you something like, what's the smallest probably A and B can be? And that sounds really weird. You're like, what the hell? Do I just calculate it? No, there's no way you can calculate that. If I just give you this. You actually can calculate it on this, but I ask you that question before I ask you to calculate it, right? It seems kind of backwards, but too bad. It's not. What's the formula for A or B? What's the formula for that? Or means basically what? And means basically what? Or means you basically add. And the reason I say basically is because sometimes you have to adjust it a little bit. So what is it? It's A plus B. Yes. So if that was 0, then the sum of these better make sense. But what's the sum of A and B?
1.1.
Holy shit. What's wrong with that? It's bigger than 1. So you're saying it's a 110% chance, right? And we're not a football team. We're not talking about, give 110%. No, dude, I can only give 100, you know. But that's more of a mental thing. We go a little bit more than I thought I could, you know, which is good. It's a mental thing. It's a follow-through thing. But mathematically, we're like, no, dude, you can only give 100%. So if I add up it as more than 100%, this must be bigger than 0. In fact, if this is 1.1, what's the smallest this could be? 0.1. Because if I do this and this is 1.1, this has to be at least 0.1 to bring it back down to something that makes physical sense. Do you guys see that? So I can tell that there must be bigger than 0 and some kind of overlap. Because that's what's going to save this from happening. I can't let that happen. That can't mathematically happen. So in part C, you figure out what's the smallest it could be is 0.2. Part D, you calculate it, and you should get 0.34, which makes sense. The smallest it could be was 20%, and we got 34%. That makes sense, hopefully. Any other questions? Yes?
It's about the homework.
Sure.
Section 3.3, 91, Part B.
Part B?
Yes.
So in 91, they give you Y and Z, and they're independent. Blah, blah, blah. Oh, so rewrite the rule using the fact that Y and Z are independent. Let's see, blah, blah. Use a rewritten rule to find probably Z if probably Y or Z is 0.71. Oh, okay. So that's weird. Alright, so the reason that's weird, I don't know what they wanted to have happen here. But Y or Z, that probability is going to be probability of Y plus probability of Z minus probability of Y and Z, right? You with me? Now here's the interesting thing. Alright, let's see if you guys are with us. What does this mean? What does that mean about probability of Y, probability of Z? I mean, what does the fact that they're independent mean? If I tell you Y and Z are independent,
One doesn't affect the other?
One doesn't affect the other. So that's the idea. Now what happens mathematically, though? If one of them happens, the other one, the probability doesn't change, stays the same. Right? So how do I capture that? So if Z happens,
Still the probability of Y.
yeah, it doesn't change. The probability of Y given Z does not change. So that's what that means. Or the other way around. So this is probably a Y given Z. But if they're independent, Y doesn't care that Z happened. It's like, oh, that's nice for you, Z. It's the same. Cool. Kids. So for example, real quick, remember the person getting off coming towards me? 50-50 chance it's a woman. The person got off a Harley, now it's much lower chance that it's a woman, right? Because not as many women ride Harleys, are you with me? But if I saw the person getting out of a Toyota, I don't know, they're basically independent as far as I know. It's still 50-50 chance. It doesn't really tell me anything. Do you see what I'm saying? So that would be, that's what it, given that they got out of a Toyota, the probability doesn't really change. As far as I know, it doesn't really give me any more. But if they came out, got off on a Harley, this wouldn't be true. The probability of a man or a woman changed now. All right, so what the hell does this have to do with anything? It's a really good question. So hidden in here, and I think the book makes this explicit. Stay with me now. What is the formula for this? Yeah, why? Yeah, probably given. I love it. All right. But what did we just say about Y and Z? So what is this? What can I put here instead? What is this? And then can't I multiply that up? So now I see what they're going. Let me stop there for a second. And we've done this. If I pick two cards, but I do it with replacement, stay with me now. So if I pick two cards and I did it with replacement, what's probably I get two kings? What's the first one as a king? Who? No, I didn't say the king of diamonds. I said a king. There's 4 kings, so 4 chances to get a king out of 52. Put it back in. What's the next one's probability?
4 out of 52.
Good. And so if I put it back in, they are independent of each other, right? Whatever I pick first, the second one doesn't care because that one went back in. If I threw that first one away, now the chances to get another king are lower. She lost a king, right? But if I put it back in, they're independent. So look, that is probably king times probably king. I didn't have to change it. But if I said without replacement, now it'd be 452 times
3 out of 3.
so the second one would change. It would be the given. Probably I get a king given that I already got a king. So the only time you can just directly multiply 2 probabilities together to get the and is if it is independent, because now I can write it like that. If they're independent, I can just multiply them together to get what and is.
Depends on your definition of these.
No, it's a little too far back. All right, so coming back to this problem. So now, how do I rewrite this formula knowing this is that? I just replaced this with that. So now probably a Y or Z is probably a Y plus probably a Z minus probably a Y times probably Z. I'm not sure why I'm slowly becoming Matthew McConaughey. All right. That's statistics. I don't know. Let's all go for a ride in my car. Sorry. Really? Yeah, sure. Thanks for that. I'm an awesome impressionist. Here's my Jimmy Carter. Hi, I'm Jimmy Carter. That's a fantastic. Is that cool? Who asked that question? I mean, so now they told you in the problem, they told you what probably Y or Z is. They say that probably Y or Z is 0.71. And they tell you the probability of Y is 0.42. And they ask you to find probability of Z. So you don't know what that is. So if I plug stuff in, what do I get? I get 0.71 equals 0.42 plus don't know minus 0.42 times don't know. So this feels very algebraic. I love it. Now you're trying to solve for this. So subtract that. Right?
But what do you do with the second?
You ready? You ready? Let's replace this. What do we do in algebra when we don't know something? We call it x. All right, let's call it x for a second, right? Just to make it look more like what we're used to. So is everybody, this is problem number 91. So they asked us in part A to rewrite this formula. So I wanted to look at the and piece. If they're independent, I can write and as this, if they're independent. So then I just put that into the formula. That's where this came from. And then they told me what this was, and they told me what that was. So here I am. So the thing I don't know is here. So let me write it like x, maybe it'll be a little bit more familiar. What's a whole x minus 0.42x? Because those are like terms. What's $1 take away 42 cents? Yeah, 0.58. So it'll be 0.71 equals 0.42 plus 0.58x. That's just putting your like terms together. And I can feel some of you guys like, I don't even know what you just did at all. I can sense that. But there were two steps to this problem. The first step was understanding what they mean. When they tell you this, you should immediately write what that means. That means that. And then I investigate. That would become just this if they're independent because of what I wrote down there. And so I can replace that with, in the equation, I can replace this with just that product. Thank God I came, because they didn't tell me a damn thing about this. So there would be no way. But since I know they're independent, I know I can replace that with this. And then I can solve this for x, which is really what I want. All right, good old algebra. Algebra, it's amazing. It has actual purpose outside of algebra class. No way, Jeff. All right. Is that cool? Yeah. Maybe not cool, but understood? No? What's up? Yeah. You gave me that big head shake. I'm like, I'm not going to miss that. Don't be doing that if you're not ready to ask questions. All right, that was one of the harder ones in the homework. But the big thing that I want you to realize is, if I know that two things are independent, I know that this is true. All right, so let's do this. Any other questions from homework right now? It's okay if you do. Yeah.
Are you mentioning about that one? How do you get so it's x minus 0.42x. How do you get 0.58x?
What's a whole thing minus 0.42 of a thing? So like, what's a whole dollar minus 0.42 of a dollar?
So
0.58.
So you made x a dollar.
So what's another way to write the number 1? 1.00.
Okay.
1.00 minus 0.42 is 0.58.
Yeah.
Cool. Maybe that's just combining like terms all day long. All right. Cool. The weirdest looks. I can't read you guys. Right, that was definitely one of the weirder problems. Is trying to figure out what they're asking you to do. So if you had trouble with only that one or that one and another one, you're fine. That's one of the weirder ones. Yeah.
Homework page 268 and number 17.
Oh, okay. All right, so let me do this. Let me do this before we get too far away from this. Any other questions from probability homework? Yes. And then we'll come back to that one. Don't let me forget. If I write a note, I'll probably erase it. So don't let me forget.
Number 96.
The one about the baseball players?
Yeah.
Oh, okay. All right, so you ready? I'm going to take all this away. anytime I ask you, are event A and event B independent? Anytime I ask you this, you cannot write a paragraph and say, well, you know, some B's are A, so no. You can't. You can't. There's no way to humanly just decipher if it's independent. You have to do math to do it, to see. And of course, what do you check? Who can tell me? What is the test to see if two things are independent? We just had it up here. Yeah.
If the probability of A given B equals the probability of A.
Kick ass. And what's the English way to say this? If B happens, then A don't give a shit. Right? Is the technical term. Right? But that's really the idea. Given that B happens, did A care? No, it's still the same thing. Probability of A stays the same even if B happens. It just doesn't care. Right? So if somebody in Russia right now stubs their toe on a potted plant in the corner of the room, will it affect what I do the rest of my day? No, it's independent. Right? That would be very strange and specific psychic ability to have. Someone just stubbed their toe in Russia. Sorry. Alright, so on this problem it says event A is the hit was made by Hank Aaron. And event B is the hit was a double. So you figure out what's the probability of hit by Hank Aaron, hit by Hank, given it was a double. You figure out that probability, and you compare it to what probability?
Hit by Hank Aaron.
Beautiful. You compare hit by Hank Aaron given double, and you see if it's equal to probability hit by Hank Aaron. Does that make sense? I mean, that's it. Whatever A and B are defined to be, that's what you check to see if they're independent. If that's true, if that equality is true, they're independent. If that equality is not true, they're dependent. Now, to be totally honest, in the real world, we give a little leeway. They don't have to be like perfectly the same. They just have to be kind of close. But for us right now, we're going to say they're going to be the same. They have to be the same to be independent. Is that decent? Yes? Who asked the question? There. They're cool? Okay. Yeah.
Would it still be dependent if it was double?
How do you mean?
Would it be independent if it was P double?
Okay.
Instead of P hit by A.
Okay, so either you can check out this, or you can check out probably as a double, given it was hit by Hank. You have to check to see if that's equal to what? Probably as a double. Either way, you could do either one. Probably A given B is equal to probably A, or probably B given A is equal to probability of B. You got to see if the first dude is not affected by the second dude. So you compare. If I knew this guy happened, I compare what this guy is now versus what he is by himself. Is that cool?
Yeah.
So what is the answer of the choices?
I don't know. So they give you this big, ugly, I'm trying not to do the, you should be able to do the work of each of these, but they give you this big table. We'll do one of them here. It's coming. All right. I like that. That was awesome. What is it? You guys know Yogi Berra? Mm-hmm. Passed away. He said, I didn't say everything I said. All right, so being made by Hank Aaron and hit being a double. So can we do probability it was a double? How would you get probability was a double? What is that? They've done all the totals for you, which is nice. What's the probability it was a double?
Would you? 1,577.
Yeah, so probability is a double. It's 1,577 doubles out of 12,351 hits, or whatever that is. Somebody do that for me. What about double given that it was Hank that hit it? So given that it was Hank, so what goes on the bottom?
Hank's hit.
771.
Yeah, so out of Hank Aaron's hit. So I know it was Hank Aaron that hit it. So out of 3,771,
624 are.
624 are doubles. That's how you do the conditional probability, right? So somebody did that for me?
1270 or 0.1277.
And what's this guy? What was that? 3771. Yeah. 620.
0.1655.
Are those the same? Are those the same? No. So are they independent or dependent? Dependent, exactly. If I tell you it was Hank Aaron that hit it, the probability that it was a double increases from almost 13% to almost 17%. Right? So it did change. The probability that it was a double cares if it was Hank Aaron or not that hit it. I don't mean baseball suddenly are conscious or something. I don't freak out about hitting them. I'm hurting these poor things. But does that, when I say care, I just mean that the numbers change. So it cares in that way. Yeah.
So it would be the same number if it was independent?
Exactly. If they were independent, this would be 0.1277, this would be 0.1277. In the real world, if this was 0.1277 and this was 0.1281, that's close enough to say that they're roughly independent. Right? But for us, we're going to make it really clean, and we're going to say if they're not the same, they are dependent, which technically is true. Okay, maybe. But I mean, if this was 1277 and this was 1276, you're like, dude, that's close enough. All right, but this is a almost a 4% change. That's obvious that there was a change, right? Okay, I like it. All right, so let's do this. I want to talk about what can be on your formula sheet, so you can actually create your formula sheet as we do this. If you have anything else on your formula sheet besides what I say you can have on it, you will lose points. So if there's something you think I missed, you got to let me know. And before I get too far away, too, if you look at Part E on number 3, that's exactly the kind of thing I'm going to ask you. Are this and that independent? So you can see what I checked. And for that sample, the probabilities were different, so they're dependent. And I'm so nice, I'm going to actually make you calculate what you need. You just got to go back and reference them. You just got to go back and get them. I'm going to make you do the work you got to do. You just got to know which ones to look at. In this one, it was Part A and Part D. That was the work you needed, right? All right. So obviously, we can have, this is all about probability, this one. We can have this. We already had this up here. What's the formula for this? Let's start here. What's the formula for this? We just had this one up on the board here earlier. Had Y's and Z's, but it's the same thing. What goes on the bottom? The given. Yeah. Good. So if it's given that it's B, what's the only way that A can happen if it's the A's that are in B? Because I just told you B happened. The only way. So if I look at, I don't want to do that. Right? The grammar gets easy to get lost in there, but this board is the formula sheet. This board is not. Right? So if I had a visual, if I tell you that B happens, what's the only... So something in B definitely happened. What's the only way that it could have also been A? Is if it's the A's that are here. And that is A and B. That little piece here is A and B. Is that cool? It's a nice visual of why the formula is that. Okay. So what's this? I just take this formula and I multiply that up. So I get probability of B times probability of A given B. So we used that one earlier today. So if A and B were independent, this would just be probably A and B equals probability of B times probability of A. Because that would be probability of A. Let me say that one more time. If A and B were independent, this would just be probability of A, because B wouldn't change it, right? So then and would be exactly the multiplication of the two probabilities. If A and B were mutually exclusive, what would that mean this is? If they were mutually exclusive, this would be 0. So then the OR would be just the straight up addition of them, right? So this is an adjustment if it's not mutually exclusive. This is an adjustment if it's not independent. That's what those are. And notice how everything I just said was not written on this board. So none of that better show up on your formula sheet. Right? So any other formulas you think you should be able to have on there related to probability?
Would mean me and might be on it?
No, this is just probability. And if you want to, you can just kind of add on to the formula sheet you use for test 1. Just keep adding on. You don't need the other formulas, but if you just want to add these on, because then you can have a formula sheet for the final, or a collection of formula sheets for the final. Right? Either way you want to handle it. So any other suggestions? There weren't that many formulas, really.
Would probability of distribution, or probability distribution tables be on there?
Oh, chapter 4, no. Just chapter 3.
Or just
The chapter 4 stuff, the X and the P of X stuff, that's going to be on the next test. And I know the next test sounds like it covers a lot. It covers chapter 4, 5, 6, and 7. But each of those have like 2 or 3 sections. And in the old book, chapter 4, 5, 6, and 7 was chapter 5 and chapter 6. So this book just takes all the ideas and splits them out into all their own little chapters. You guys kind of with me? So it's not going to be like this monster-long test that nobody will finish. Right. No. It'll just be a normal-sized test that some people won't finish, as always. All right. So that's all you can have. That's it. Any other notes? Any other pictures? Anything else? Don't turn in a formula sheet with your test that has been ripped in half or has anything marked out. I'll just have to assume that those are notes that were there that you shouldn't have had, and I'll take some points off. So don't be mean to yourself. Okay. All right, so let's get back into chapter 4. Well, before I get too far, remember when we did the table? Like if I ask you this, if I ask you, what's the probability that it was a triple that was hit by Jackie Robinson? I want to know the probability it was a triple and it was hit by Jackie Robinson. Do I need a formula? No. How many triples were hit by Jackie Robinson? So 54 out of? No, I didn't give it given. It's not a given.
12,000.
Yeah, 12,000. So if I pick a hit out of this selection of hits from these people, what's the probability it was a triple that was hit by Jackie Robinson? So it could be any of these. The only time the bottom is not this is if it's a given. So if I said given that it was a triple, then the bottom would have been 583. All right. Okay. Cool. So what we did last time, and let me make one more. Everybody got the handout from that last time, chapter 4. Yeah. All right. Cool. So we worked on that last time. If there's no specific questions, I think. Wait, who had? Yes, good. So your question's a good one because I like you. It was 4-1.
Yeah.
Wait, number what? Number 17?
Yeah.
Oh, and by the way, oh shoot, they use this, which you could use too if you want to, or you can use the formula that I showed you in class. You remember we used a slightly modified formula in class? You guys know what I'm saying?
Yes.
All right. Or you could use this. I don't care. They both are the same formula, so it doesn't matter. So number 17, though, gives us this here. Oh, not 17. Well, it wasn't 17. What was it?
Page 268.
Yes.
17. 70.
Oh, 70. All right. Here we go. All right, sweet. I like it. So here's the nice thing with... let me just give you a couple of things here. So I'm not going to do a whole problem out, but how would you get the mean? What's the formula for the mean?
It's,
Yeah, I would add up what? No, careful. If it's given to me as xp of x, I don't add them up divided by a milliard because it won't work.
it's like an E symbol, X, P of X.
I like it, right? So that's the formula for the mean. If you're given a probability distribution, you with me so far? I'm working my way up to your question. I got to say something like, dude, so I don't think I've said this yet. If you had to guess, so let's say I had, so I asked somebody how many TVs they got, and blah, 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 and I get the mean is 2.7, and I say, what's your best guess for how many TVs that guy's got? Your best guess would be like 2.7, which sounds weird, or 3 if you wanted to round it. Your best guess will be the average. Does that make sense? So that's why we actually call the mean, the expected value, and you want to see something cool? What are the first 3 letters in the word expected? And what does it look like that? Alright, good, let that happen. Alright, so the mean is also known as the expected value. And the formula actually tells you that's happening. And why does it make sense? Because it's the value that I would expect to happen is the average. Or close to it. Stay with me. So this problem, it says, theater group holds a fundraiser. What are you interested in here? That is a weird question. So a theater group holds a fundraiser. It sells 100 raffle tickets for $5 a piece. Suppose you purchase 4 tickets. Cutting off the prize is 2 passes to a Broadway show worth $150. Okay. What are you interested in here? So if you were actually going to purchase these tickets, what would you be interested in? Like if you play the lottery or something, what might somebody be interested in? The prize, good, right? But also I'd be interested in, how likely is it I'm going to win that thing, right? I mean, if it's a 1 out of 2 chance, I mean, hell yeah, I'm in. It almost doesn't matter what the prize is. If it's a 1 out of 7 million chance, well, the prize better be kind of big for me to get into that. Does that make sense? So that's why when you have a $250 million prize, possibly, your chances of winning are 1 out of 7 million or something crazy. But still, a lot of people play because like, hey, it's worth it. If the prize was $3, not everybody would play. If it was 1 out of 7 million chance to win. All right, I like it. So what am I interested in here is the probability of winning somehow, right? Or what can I expect to win? The random variable x. So what would that be? What do you think that is? So see, it sells 100 raffle tickets for $5 a piece. tickets, you buy 4 tickets. The prize is 2 passes to a barber shop. Prize, there's only one prize, 2 passes, and we'll just call it, it's basically $150 prize. So this is kind of silly. This part B is a little silly. I know you guys are like, what the hell? But how do you figure out what the variable is? You think, what could people be doing? Not really. Or?
Losing.
All right, good. So those are the possible outcomes, right? So you could win or you could lose. Now put some values on that. If you win, I've got to be a little careful. We bought 4 tickets, right? So how much did we pay for that?
$100.
So we paid $20. So the 2 outcomes. Let me see. I like it. Okay, good. So the 2 outcomes are, in words, they're win or lose. Stop there for a second. So the variable is how much you win or how much you lose. Just how much you win, let's say. If it's negative, that means I lost it. So if I lose, if my tickets don't win me anything, how much did I make?
0.
Not 0, negative 20. Because I'm 20 out. Right? If I just didn't play the damn game, I'd be 0. I'd be everybody's breaking even that doesn't play. So I'm out. Well, not if you win, Jeff. There you go. Out $20 if I lose. If I win, be careful. If I win, how much do I win?
130.
$130. I like it because I lost 20 in the first place. All right, let me stop there for a second. So what we're doing is we're constructing an X P of X table from a situation. Right? They're not giving me the X P of X table. We're making it. So we first got to figure out, well, what are the possible outcomes? Right? Either I win or I lose. Convert those to math. All right, 130 or negative 20. Those are the outcomes. Those are the values of the variable. That's part C. PDF is not, you don't need Adobe Acrobat for it, but it's the probability distribution function. I just call it a probability distribution. You guys with me? So I just need to make the X P of X, and which is what we're doing on the way here. So what's the probability of each of these things? Remembering that we have bought 4 tickets, right? How many tickets are they going to sell? 100. I like it. But what's the probability that I win then? So what's probably that any ticket wins?
1 out of 100.
Yeah, 1 out of 100. Right? So the probability that a ticket loses, 99 out of 100, right? You guys still with me? Alright, I like it. But I bought 4 tickets. I bought 4 of the tickets. So what's probably that one of those tickets wins? 4 out of 100. So out of 4 out of 100 chance, which leaves what over for me losing? 96 out of 100. I like it. Let me stop there. Because if I bought all 100 tickets, what are the chances that I win? 100 out of 100. What's the chances I lose? 0 out of 100, right? That would be the real dork. Like, thanks for your money, but shit. Other people want to try. Let's print up some more tickets. Alright, let me stop there for a second. You guys still kind of with me here? How many guys have car insurance? Alright. Thankfully, hopefully everybody that raised a hand, there's not more of you that are driving. If anybody left their hand down, don't be driving. And if you are driving, stay the hell away from me. But when you get your bill, when you hit age 25, I'm pretty sure it's still 25, magic things happen. So what they do is they construct a table, and the table is the probabilities that you'll get in an accident and the amount of money it's going to cost for that accident. So they have these tables that they make up, and it's based on age. Right? So below 25, the probabilities are one thing, based on actual observed data. Are you guys kind of with me? And so they figure out, they're going to do everything we're about to do. They figure out what the expected amount they got to pay out, and then they set their premium a little above that so they make a profit overall. Do you guys follow? That's exactly how they do that. Any insurance does it basically that way. All right. And of course, when you hit 25, the probabilities change based on observed patterns, because obviously if you're below 25, some of those people are believing that they can do whatever the hell they want to. Right, now I sound like an old man.
What the hell's wrong?
But I used to be one of those people, and yes, I probably needed to pay extra insurance. Anyway, so that's one immediate application of this, is how an insurance company sets its premiums, and why at 25 you suddenly wake up and you're like, oh, that's how you drive. Okay, I get it. No, that doesn't really happen, but it's just the way that they calculate things. So what do I do next? So we've done the part D. And now I want to figure out my expected average winning. So I want to calculate the average. And then I'll explain what it is once we get it. But now that I've got an XP of X table, I know how to get the average. How do I get the average? What kind of column do I need? Sorry, I cut you off. Yeah, XP of X. So what's 130 times 4 out of 100? Okay. And then what's negative 20 times 96 out of 100?
Negative 19.2.
So if you add those up, you'll get a number, and I'm going to try to explain what that number is. And actually, what is that probability-wise? What's the term for what we get? If we add these up, I get the what? Well, you get what? You get
negative 14.
That's crazy. But what is that? That is the mean, or expected value. Let me let you guys. So see, this is exactly what I said. We constructed our own XP of X table from the situation they gave us, and then we attacked it the way we know how. It doesn't say anything about standard deviation, right? So I don't have to worry about doing another column. I just have to stop at the mean column, right? So what the hell does that mean? I don't know. It means if you play this kind of thing a lot, you would average a loss of $14. So maybe you'll win once or twice if you play it a lot, but you're going to lose a lot more times. So what's funny is if you calculate the expected value for some lotteries, they come out to be like 17 cents. Which means if you play the lottery a lot, you might win, but you have to play so much until you're able to win that if you add up what you had to pay with what you got, it's an average of 17 cents left over at the end. Or a slightly better way to look at it is, one lottery drawing has millions of people playing, right? So maybe one person wins, and if you average what they won with what everybody else had to pay, what they lost, you end up with 17 cents on average. You kind of with me? So if you do this for a situation, and this comes out positive, that means it's a good thing to do in the long run. If it comes out negative, that means it's a stupid thing to do in the long run. Right? Now, true gamblers would say, I don't give a shit what that is. Right? Don't tell me the odds. Right? I'm going to do it because there's a chance I could win something. But if you're playing poker, and you're able to calculate odds on the way as you're playing the game, you know on the long run what's the right approach to take. That doesn't mean you're going to definitely win. There's nothing, and that's why people go, statistics ain't worth shit, because they want definite, what exactly should I do? And I'm like, that's not life. Math can't do magic. The hell. But this tells you, if you do this over and over, you might lose in this round, lose in that one, but then you'll win here. And your average, if it's positive, you'll actually make money. I don't know if you guys are with me. So it kind of gives you an overall strategy to follow, is what this does. It's a long-term thing. It's when you do an expected value from this kind of thing. All right. So an insurance company, they might have to pay, like somebody might have this huge accident, and they have to pay like a ton of money. But why do they not really care? Because they have thousands and maybe millions of other people paying them, and they're not having accidents. So they calculate ahead of time, according to the probabilities, how much do we want to charge everybody so we can handle it if these guys have big accidents. We can handle that. We're like, oh, no problem. Here's a lot of money because we got a big old room full of money back here. Right? That's insurance in a nutshell. Basically, AIG. Look them up. All right. Is that?
Yeah.
All right. It's got to be all right because you basically did the whole thing. I really need you to do that at all. All right. Anything else from homework? All right. So the rest of the day, I want to focus on the next section, which is talking about binomial probabilities. And I am going to attempt to explain. And one thing and again, this textbook is free. Obviously, there are typos in it, and there will be things that I disagree with myself. And this is a big one. In this section, they don't talk about the actual formula. They just say, here, go push these buttons in the calculator. I think you know my feelings on that. So I'm going to show you the formula, and you are going to need to use this formula. You can check yourself, and I'll show you how to do it, because I always show that. You can check yourself using the calculator, push some buttons, and bam, the answer shows up. But you must set up the formula to get your answer. All right. You took the wrong teacher if you didn't want to do that. All right. So here's the idea. The idea is actually kind of nice if you let it be. So what's binomial all about? What does that sound like?
2.
I love it because in math, pure math, a polynomial that we call a binomial has how many terms in it? 2. It's great. So binomial probability in statistics references a situation where there are exactly 2 outcomes. Not at most 2, not at least exactly 2 outcomes. So flipping a coin is an obvious one, right? Because then there's only tails or heads. Rolling a die could also be one, believe it or not. My 2 outcomes could be a 5 or not a 5. You guys still with me? So in that sense, everything can be looked at as a binomial if it's the right way that I'm looking at it. Right? That's the way I want to look at it. Maybe. So what I want to do is, let's say I'm looking at left-handed people, and I'll call this L. And just to include everybody, I'll say not left-handed. We'll call those, let's go ahead and just call them L not. Because you might be ambidextrous, right? Yeah. I'm both. Well, that's nice for you. Alright, so I don't want to do left and right. Alright. So let's say I pick, and here's the thing. The last time I looked, the probability that somebody was left-handed is about 11% chance. How many guys in here are left-handed? Anybody? I'm not. 2, okay, 2, and there were 40 people in here or something? 2 out of 40 is 1 out of 20, is 5% chance. Yeah, don't freak out, I'm not, there they are! No, sorry. So this is a, so let's say I'm looking for left-handed people. So, what I'm about to say is if I had 5 people, what's the probability that exactly one of them is left-handed? So I'm looking for a left-handed person. You with me? So I'm going to call that a success. All right? So be careful. A success doesn't have to be a happy thing. A success could be a dead body if I just happen to be, if I'm walking through a battlefield, let's probably find a dead body. Right? That would still be a success just because that's what I'm looking for. Right? So what we do is we give this a slightly better notation. We call this P. Little p is the probability of success. Alright. Because if you find it, you're like, oh, cool, and you just pee a little bit. was just for me. It's fine. I like it. So what's probably not left-handed then? You guys can do it. It's got to be 89. Kick ass. It's got to be the rest. These two have to add up to be 100% because they're opposites of each other. And incredibly enough, I use the letter Q, and I'm going to call that one a probability of failure. Not because I think right-handed people are failures, mainly because I am a freaking right-handed person, but just because I'm not looking for right-handers in this problem that I'm going to talk about. Right, so far, so good, right? So there's a little bit, there's the P and Q is really the only new thing so far. That's the symbols we use for the two outcomes. One I'm going to call a success, and the other one I'm going to call a failure. All right. So here's the idea. If I pick 5 people at random, I think you're basically dead, poor little dude. Pick 5 people at random. I want to know what's the probability that exactly one of them is left-handed. So that's what I want to figure out. And why is this different from what I've done before? This feels like something we've done before, but when I said like the probability the first poker chip is blue, and the second poker chip is green, and the third poker chip is red, that wasn't as, that was very specific. Blue, and then green, and then red. If I just said, what's probably to get at least one green, or exactly one green, where could the green have been? It could have been first, or second, or third. You kind of with me? So this is more general than what we've done before. And we didn't have the math to do that until today. We will figure it out. We'll figure the math out. So what could happen then? Let me represent left-handed people, of course, with little p. Right? Non-left-handed people with a little q. So somebody tell me, if I pick 5 people at random, what's one thing that could happen that matches what I'm looking for?
One person being left-handed.
That is what I'm looking for. But there are many ways for that to happen. If I pick 5 people, maybe the first one is left-handed. And then the other 4 have to be right-handed. Or else I wouldn't count it. Right? So don't get too wrapped up with, why does that have to happen? No, I'm just going to count what matches what I'm looking for, right?
So would that
of
be
course.
like 1 over 5?
No. Be careful. So that would be P with 4 Qs. Let me let you absorb that. So what would that mean? That would mean the first person is left-handed and the last 4 are not. That's one way to do this. Now watch. Why am I multiplying here? Isn't that what that represents? Because I want the first person to be left-handed. No. Say it like a whole sentence. I want the first one to be left-handed.
And the rest.
And what does and mean? Basically means multiply, right? And if the first person I pick is left-handed, does that change what the second person is? I'm like, oh God,